I'm Antonio Guimarães. I'm a postdoc at INDEA in Madrid. Today I'm going to present this paper called the Fast Amortized Bootstrapping with Small Keys and Polynomial Noise Overhead. Okay, now let's start. Let's start with the basics. I think for this community, this should be very easy. We have here the way that we usually do FHE. We have a ciphertext, we do operations, noise grows, we do a bootstrapping. The bootstrapping, it doesn't reset completely the noise. It has some noise there. And we would, of course, like to have the smallest noise possible for the bootstrapping, such that all our parameters for the FHE scheme are also small. This will be the focus of this talk, to present a bootstrapping that introduces noise that is only polynomial on the secret level, but that at the same time it has some of the advantages of other bootstrapping schemes that introduce way more noise. FHE branches. Usually we divide FHE schemes in several ways, like talk about generations of FHE or branches of FHE. This is all very arbitrary, so this is just really like people usually do, but it's very arbitrary division. Usually we think about these two branches. On the top one we have schemes such as BGV, BFV, and CKKS. And the bottom one we have GSW, FIL, and TFHE. They differ in many ways. For an application, for example, one of the differences is that for these top schemes, you can work with very high capabilities of SIMD, so single instruction, multiple data. Essentially, you can do a lot of multiplications at once, a lot of additions at once, a lot of bootstrappings at once. And that means that usually we have a relatively high latency. So doing the full operation will take from beginning to end will take some time. But you also have a high throughput because you're doing operations over a lot of data at once. Conversely, and also in this aspect, you have that these other schemes, they have very limited capabilities for SIMD, for batching, but they also have a very low latency because they operate over one message and they operate very quickly. On this aspect, I would say that the top branch has more advantages, at least at first. That's obviously subjective, but the bottom branch would be just low latency. But this is not the only difference between them. There are way more differences, and one very important is in terms of noise and parameters. And it's actually one of our focus here. To understand the difference between noise in these two schemes, I will briefly go through the two types of multiplications that we do. I'm showing this image, it's a high-level abstraction. But essentially, let's say that you want to multiply two messages, and you have these two types of multiplications, BFV-like and GSW-like. The way that the noise behaves in these two types of multiplications is different. So if you just do this first multiplication, we will have more or less the same noise. So here you had some amount of noise, it doubled, same thing on the other side. But once you continue to do multiplications, you will notice that in BFV-like multiplications, you have a multiplicative behavior. Meaning, if you're multiplying 3 messages consecutively, you'll get triple the amount of noise in numbers of bits. Again, I'm simplifying things here. You could do mod switching, other things, but in the end, relatively to the original modulus, you have that the noise accumulates multiplicatively. GSW behaves differently. The noise is quasi-additive, which means you will add these two noises plus some constant that depends on the smallest of the noises. So when you do this first multiplication, you just add in plus the constant, since these were the same amount of noise, you get double the noise. But once you receive a new sample that has a small noise, you can do this multiplication, and what's happening here is that you're adding these two noises plus a constant that depends on the smallest noise. So you cannot see, but there is an additional bit of noise there. I'm zoom in here. And this is a very small increment, and you can continue to do many, many multiplications as long as you have this asymmetry. So you always want to have one ciphertext with small noise. And this is what will allow us to build bootstrapping with a very small noise as well. Okay, the consequences of that to the FHE branches. This first branch of FHE, it uses BFAV-like multiplication, therefore multiplicative noise. And the bootstrapping schemes that operate over them will, the result of that is that they will have a noise that is super polynomial in the security level. Meaning, let's say you select the dimension n linear in the security level, your modulus that you will need to perform this bootstrapping will generate this super polynomial in lambda. So something like this, for example. On the other branch, the GSW multiplications, they allow you to have this quasi-additive behavior. And thanks to that, you can have a bootstrapping that only has polynomial noise. So again, you select your dimension linear in the security level, and you get something like this, quasi-linear or even linear in the security level, also in terms of noise. This is another difference between these two branches. And one question, of course, is why does it matter? And there are actually multiple reasons for it. The first one, and perhaps the most important one, is security. Essentially, FHE and LWE is based on problems, on reductions to problems such as gap SVP. And these reductions, they have approximation factors. And in very high level, if these approximation factors, they depend on the modulus, on the asymptotic relation between the modulus and the security level. And what you have is what this image shows. If the approximation factor is O of 1, we would have an NP-hard problem. If the approximation factor was exponential, then it would be broken. We can solve the problem in polynomial time. The schemes that I was showing, they are in this middle. And essentially, having a polynomial noise is strictly a weaker assumption than having super polynomial noise. So these schemes, since they rely on super polynomial noise, and again, in very high level, you could think of that they could be broken without the other ones being, while the other ones, if they are broken, if gap XVP is broken for polynomial approximation factors, all of them would be broken. This is the motivation in terms of security, but of course, these are all assumptions, and for now, they are all holding. So we can also look at more practical and current reasons. If you think we are talking about parameters or noise overhead, and intuitively, having an overhead or parameters that are polynomial should be better than having something that is super polynomial. In many aspects, it is. When you have a scheme that is based on polynomial noise, you can have smaller keys, you can have schemes that require less memory, they are also faster in terms of latency, and intuitively, they should also be faster in general, like in number of operations per second, for example, but they are not, at least not for now. So this is one of the goals of this research, to improve the number of operations per second that we can do with these polynomial schemes, aiming at, of course, having better performance in general. So this is basically the differences between these two branches, and I think with all of these factors here, it's very clear that we would like to have the best of both. We would like to have a scheme that has the security of being based on polynomial noise, while also having the SIMD capabilities of the top schemes. So can we have the best of both? The first paper to answer to that was this paper from Micciancio and Sorrell, 2018. And it was a yes, but a yes in principle. Essentially, they established a framework that allows you to do SIMD with polynomial noise. So they established this concept of amortized bootstrapping. And they gave us basically a blueprint on how to do it, but the concrete performance of what they presented was not really practical. I will now go through more or less the blueprint presented by MSA team. And to do this, I think I should first explain also very briefly how the LWE bootstrapping, so the non-amortized version of the bootstrappings that work with polynomial noise, how do they work, and what are the building blocks that we are also going to use for our work. So detailing a bit more this line of work, the very first bootstrapping scheme to have polynomial noise was actually BV 2014. We usually put GSW on this other branch, but originally GSW also had a super polynomial noise. Nowadays we know how to do GSW with polynomial noise, of course, but the very first was BV. BV, when I say BV 2014, we probably think of the BV leveled scheme. This is a different paper. It's same authors, same years, but a different work. So it's this paper. And from the title of this paper, I actually like the title of this paper a lot. You can clearly see the motivation that started this line of work. You wanted to have lattice-based FAT as secure as you have public key encryption. And while the motivation here was security, the works that followed, they are already focusing on performance and really having the smallest possible latency. And you have Phil, for example, which was able to do bootstrapping less than 1 second, and then TFHE in less than 100 milliseconds. So polynomial noise LWE bootstrapping. This is basically the bootstrapping of Phil, TFHE, and all these other schemes. I will explain in high level because my focus here is really on the components that we are going to use later. The basic idea is that you have an LWE encryption. It's given by this equation. And if you want to decrypt it, you want to compute this on the other side. By the way, just a question. Do you see my mouse? My pointer?
Where is it? Yes, I can. Yeah, it's very small, but yeah, I can see it. Yeah.
Okay. So the goal is to compute this homomorphically. You want to compute the LWE decryption circuit homomorphically. And the way that this bootstrapping works is that you will first compute the linear part of this, so B minus the product of A times S, and the exponent of an RLWE encryption. So an RLWE encryption, I encrypt polynomials, you want to compute this. This, as you can see, is basically the message times some scaling factor that comes from the encryption, plus the noise. This is the most challenging part on this type of bootstrapping. And once you have this, extracting back the message and finishing the bootstrapping is relatively easy, at least from the computational point of view. Again, in high level, what you do is essentially you would build some kind of lookup table. You would embed this lookup table in a polynomial, and now you can compute just a multiplication between this polynomial and the encryption that you have. By doing that, you are essentially rotating this polynomial that encrypts the lookup table in a position that is given by your message plus your noise. So in this example, you would have that the first position, that the coefficient, the constant term of the polynomial encrypted by this RLWE sample is encrypting the position n minus n plus e of the lookup table. By knowing that there are some bounds to the noise, and you can use these to move this lookup table to the position that you want, you extract it, and you have your bootstrapped message. This is basically how TFHE and Phil work, so it's nothing new here. The main point of all of this is that the challenge is in computing this first step. For the LWE bootstrapping, this is done by what is usually called blind rotate. So you usually start just with a accumulator and you use conditional multiplexers, controlled multiplexers to compute every term of this inner product. This is a process that exploits that asymmetric behavior of RGSW multiplications. And through this process, you can have a bootstrapping that only introduces linear noise. Now, so this is basically how the LWE bootstrapping works. And when you move to amortized bootstrapping, when you move to MS18, the idea of MS18 was essentially to evaluate this same AP style bootstrapping, let's call it, but with RLWE encryptions. So if in the normal TFHE field bootstrapping, you are computing the decryption equation of a LWE ciphertext in the exponent, now what you would like to do is to compute the decryption equation of an RLWE ciphertext also in the exponent. Of course, this thing that I wrote here doesn't make sense. I have one polynomial to the exponent of another, so what they actually do is very different from this, but the intuition would be this. Let's try to improve this a bit before we continue, because here we have 2 rings now. Before, we're decrypting LWE samples, which are defined over the integers, using RWE samples, which are defined over some polynomial ring. Now we are working with 2 polynomial rings. So just to differentiate between these 2 polynomial rings, I will always represent the input ring, the one that represents the input RWE sample using the variable y, and the output ring with the variable x. So putting in this notation, what we would like to compute is this. So x with the decryption equation of RWE in the exponent. Again, that doesn't make sense. We still have one polynomial to the exponent of the other. So what MS18 actually proposes is that you have a list of RWEs such that each element of this list is encrypting in the exponent a coefficient of this polynomial in y. If we remember the normal LWE bootstrapping, once you have something of this format, so once you have x to the n plus e, you can just continue the normal bootstrapping, multiply by the lookup table, and extract. So the real challenge here in MS18 is just how to compute every element of this list, or how to evaluate this b minus as in the exponent of a list of RWE samples. There is a trivial solution for that, which is this one. Like you can compute each element of this list individually, but that would not give you any gain. It would not give you any amortization because this costs n, and you have n elements in this list. The observation from MS18 is that the goal is to compute b minus as, and the costly part is a times s, which is a polynomial multiplication. So you can have something that has a sublinear cost per coefficient if you do this polynomial multiplication with some efficient multiplication algorithm. So we could do an FFT, an NPT, Karatsuba, any efficient multiplication algorithm for polynomials would work and would give you something that is sublinear in the cost per message. The challenge is that you not only have to homomorphically evaluate it, but you have to homomorphically evaluate it in the exponent of the output ring, the exponent of x. So you need an multiplication algorithm that can be evaluated in this way. Since we're talking about doing things in the exponent, it's good to define which operations we can do. So we can do additions. So if you have x to the a and x to the b, if you want to compute x a plus b, you can just multiply the two. Multiplications will become exponentiations, which, I mean, it's probably possible, but we don't even want to think about it. And we can do scalings. We can multiply by constants, clear text constants, by using automorphisms. Based on these operations, what MS18 proposed was to actually use the Nussbaumer transform to compute this efficient polynomial multiplication. I will not get into details, but essentially the Nussbaumer is something that you use when you don't have roots of unit, for example, when you want to do something that is entity-like. It's very good in terms of operations. You don't need roots of unit, you don't need multiplication, it's asymptotically efficient, but it's really not practical. You have really huge constants that doesn't make this scheme practical at all. On the other hand, this whole thing that I explained about how you evaluate this AP-like bootstrapping for RWE is a blueprint that allows us to continue and try other ways of evaluating this polynomial multiplication in the exponent. So the Micciancio and Sorrell was presented in 2018, and for about 5 years we have basically nothing, until the first implementations of this, which came from GPV 23. Now, the difference from GPV 23 to what MS18 did is in 2 things. One is that before they could not evaluate entities because you need specific parameters for evaluating an entity. Specifically, you need roots of unit. And if both your input ring and our output ring are defined over power of 2 cyclotomics, you would not have roots of unit in the exponent, because the modulus and the degree of the entity would be both power of 2. So GPV work around that by defining a scheme that works with what it's called circulant LWE. So you work over this polynomial x to the p minus 1. And with that, you can have entities and you can have a more efficient implementation. Different from Micciancio's, this one is more practical, or at least feasible. You can implement it and you can have very small gains for a very large size of parameters. But it's not really a fully practical implementation. Specifically, the smallest key size in this work was 60 gigabytes, and that was for, I think, 3% improvement over non-amortized TF-HE. Finally, this work. So one thing that I think it's very clear is that in this field, we are stepping towards simplicity. So MS-18 was using Nussbaumer, which is a quite unusual multiplication algorithm, at least in FHE. GPV was already using the usual entity, but they had to work over somewhat unusual rings, specifically in circulant LWE. And what we do in this work is to go even simpler and work with just a sparse polynomial multiplication. So the goal is the same. We want to compute b minus as in the exponent. But we will start with two additional assumptions. One is that S is sparse, and just for now that S is binary. Later we will remove this assumption that this additional requirement that S is binary. Clearly, this multiplication, if we have a small amount of indexes in S, so we have a small amount of non-zero polynomials, monomials, we can compute it like this, which can be represented like this. So a multiplication between A and S can be represented by H, let's H be the Hamming weight of S, monomial times polynomial multiplications. Now, a monomial times polynomial multiplication can be computed in time n times h. And if you consider time cost per message, since these RLW encryptions would be encrypting n messages, the cost per message would be O of h if we are able to homomorphically evaluate this algorithm. So this is the starting point. And the point of the work, the main contribution, is really how to homomorphically evaluate this, how to get this cost, and also how to improve a bit over this cost. Okay, so how do we compute this in the exponent, this monomial times polynomial multiplication? What we do, we introduce an algorithm. I will just give the high-level intuition of how it works, but it's called MPMUL for monomial polynomial multiplication. It receives a polynomial, possibly encrypted, so it could be a list of RLWE encrypting the polynomial in the exponent, and some encryption of the monomial x to j. In practice, it's an encryption of j. We receive these two things, so this is our polynomial. Let's suppose that at first it's not encrypted. This polynomial is represented as a list of coefficients in the exponent, same as we had with MS-18. And now we want to compute this new polynomial A prime. So in the list representation, it would be something like this. So what we are doing is rotating this polynomial AI, YI, by j positions, and it's a negacyclic rotation because it's with these modulus. So at the end, we would have this list. The way that we compute this, and again, this is just a high-level intuition, is that we start with a list of that represents the original polynomial, all encrypted, all in the exponent. And we also start with an encryption bit by bit of the exponent j. What we'll do now is conditionally rotate and conditionally negate this list, all in the exponent. The negation is in the exponent. So let's say that the first bit of j is 1. That means that I have to rotate one position. That's what I'm doing. And I also have to negate the exponent of the first encryption. We do this negation with automorphisms because it allows us to multiply by any constants, any clear text constants. And in this case, we are multiplying by -1. And the conditional rotation we do using the same controlled multiplexer that is used by TF-HE, for example. So we rotate in one position and we use the CMUX to select between the rotated and not rotated polynomial. We go for the second bit, same thing over the first one, and we continue this process such that at the end we have this list rotated and negated conditionally based on the value of j. If we go back to the multiplication algorithm, we can see that this algorithm, it works, like in terms of correctness. If I'm multiplying every monomial individually and then adding all of them, I have the multiplication of A times S. And since this algorithm that I just showed, it works in times n log b, this already gives us something that is asymptotically okay. Essentially, we would have a bootstrapping that runs in times h log b, where b is a bound for the size, for the value of j. In terms of noise, noise is also, this is the noise per NP-move, so it would be h times this, which is linear or quasi-linear in the security level, and to also be okay. But there is still a problem with this algorithm. So if we expand this summation, we'll have something like this. So I'm just expanding the summation. And each call of this NP-move algorithm is, it will do GSW multiplications, and the result of them will be a ciphertext that has, let's say, GSW depth 1, meaning there is some noise there. They are not fresh encryptions anymore. When we do this addition, and let's remember we are doing things in the exponent, so additions become multiplications, this becomes a circuit with depth 2. And it's fine to have a circuit with depth 2, but that increases our parameters, and that was actually the problem that leads GPV 23 to not be fully practical. So we don't want a circuit with a larger depth. Just to remember, we want, whenever we are doing GSW multiplications, we want this asymmetric behavior. To solve this, we propose to change that equation, so this sparse polynomial multiplication equation, to this one in the bottom. What we are doing here is just really rewriting the top equation, such that now every multiplication is on one side. So when we write this using NP-move, you will not have the addition between two NP-moves anymore. What we have is that whenever you do an NP-move, you have at least one component which is a fresh encryption. And when you do the subtractions by A is a clear text, so it also does not add to the depth. With this formalization, the GSW depth, let's call it that, it's just 1. And you can have basically the same or even better parameters than normal field, no-amortized TF-HE. So this is the cost that we have with this formulation. It's the same cost as before, but noise accumulates quasi-additively with just depth 1. And for the full algorithm, you would have an amortized time that is h log b for this log b that is a bound to the value of the monomials. So let's take a closer look at what is the actual value of p. Like I said, it's a bound for the value of the monomials. But if we look in this equation or at this other equation, we can see that we are always multiplying by monomials that is the difference between two consecutive monomials of the secret key. So for this secret key, for example, it would be, the maximum value would be 5, which is 5 minus 0. And the worst case for this is n minus h, where h is the Hamming weight, which is okay, which gives us this performance, this asymptotic costs. But it can be better. Essentially, the non-zero elements, the index, the exponent of the non-zero elements of a key, they are uniformly random. And that means that we can establish a high probability bound on the value of p that is equal to n over h, O of n over h. In practice, what we usually do is take something like 4 times n over h, and we do rejection sampling to guarantee that all the keys would respect this bound. Of course, we analyze the security laws of this rejection sampling, and we consider that when computing the security level. Considering this high probability bound, we have these asymptotics, and if we assume that both n and h are linear in the security level, which is usually the usual assumption, we have that the noise of this bootstrapping is linear, while the amortized time is O of H. This can be improved. We can increase N and decrease H, and we have some freedom to do that because our noise is only linear. We could, for example, make this choice. We would reduce the amortized time, while the noise would still be just quasi-linear. And just to remember, our interest is to have the noise being polynomial, a low-degree polynomial, so we can go even further than this if we want. Generalizing it. So at the beginning, I said that I was assuming that this was a sparse polynomial with binary coefficients, but we can generalize it. And in the paper, we present algorithms for that. I will not go into many details, but essentially, we can have variable Hamming weight. So instead of having a fixed Hamming weight H, we can just establish a high probability bound for the Hamming weight. And this will add a cost that is given by 1 over log 2 of b, which in practice, it's around 10%. You can also work with ternary secrets, which will also have a cost of around 10%. And you can work with arbitrary sparse secrets, meaning it's sparse, so there are a lot of zeros, but the non-sparse positions, they can follow any distribution. In this case, you would have a cost of 20%. These are costs if you look just at the algorithm with the exact same parameters and changing the key. But in the case of ternary, for example, once you go from binary to ternary, you can work with smaller parameters, and these smaller parameters, they compensate for this 10%. So as I will show the results, we actually get very good results for ternary, even though there is this additional cost that comes for the algorithm. To the full construction, usually we are talking about an RLWE bootstrapping. For now, I was talking basically the RLWE version of these AP-like bootstrappings. But in practice, what we have is that we can also use this type of bootstrappings to bootstrap several messages, several LWE messages at once. In fact, this is where the name amortized bootstrapping comes. The idea is that you're amortizing the bootstrapping of several LWEs. And what you do for this is basically you have a packing algorithm that packs all the LWEs into an RLWE. You have the bootstrapping, and finally you have the extraction to several LWE again. Our method, it's very generic in terms of packing. We accept any types of packing, and there are many in the literature. We also introduce a new packing in this work that has less noise than what existed before, but it's also more expensive. So it's kind of a side contribution that we find it interesting because it's very similar to how our amortized bootstrapping algorithm works, but it's not something that is really practical, at least for now. Finally, another thing that changes in our bootstrapping is that usually when we're doing few at your FET, you have this kind of workflow. You go from a small dimension ciphertext, you bootstrap it, you have something with high dimension, and then you do a dimension reducing key switching to go back to your original dimension. Our bootstrapping, the cost doesn't depend directly on the value of n, it doesn't depend directly on the value of the dimension, the amortized cost. So you don't need to reduce dimension. We only need to reduce the Hamming weight of your associated key. And you can actually have the bootstrapping reducing dimension, for example. Finally, to the results, we test for binary, ternary, and arbitrary keys. I'm showing the parameters here, and some interesting observations is that even though we're doing a bootstrapping for RLWE, we are able to work with very small modulus. This value Q over sigma, which is modulus over noise. If you go for KKS, for example, it would be something like 100 bits, and here we are working with something between 15 and 24 bits. And so this is a very big difference, even with a very large number of messages. Another thing that to note here is that we also have this value delta, which is a security loss due to the rejection sampling that we do to compute the bound B. This security level is already considering the original security level minus the security loss delta. Detailed results, I will compare with other literature with non-amortized bootstrapping in the next slide. Here, I want to highlight more is the behavior. If we note, for example, the difference between binary and ternary, even though there is that additional 10%, the time is basically the same. And the reason for that is because ternary allows us to use a smaller Hamming weight for the same secret level. So in the end, we can work with either key at basically the same performance. Another thing to notice is that as we increase the number of messages that we are bootstrapping, which is the input dimension, the bootstrapping key size actually decreases because it only depends on the Hamming weight and not on the input dimension. Comparison with previous works, we compare with two main works that are our references. The first is TF-HRS, which is the non-amortized version of the bootstrapping. So TF-HRS is bootstrapping just one message. It is, of course, much faster in terms of total time, in terms of latency. But when it comes to amortized times, we have gains, if we look at 8-bit messages, for example, which are almost 40 times in terms of amortized times. We also have much smaller keys because our key doesn't depend on the dimension like the TF-HRS one depends. Our key only depends on the Hamming weight, so we have keys that are almost 50 times smaller. Compared with GPV, which was the previous work on amortized bootstrapping with polynomial noise, we also have very significant gains, especially in terms of bootstrapping key size. We reduced from 6 to 3 gigabytes to at most 70. We also test and benchmark for small messages, like 2-bit messages, where the gains are smaller because the amortization is smaller, but we still have gains from 2.5 to 6.7 times. And finally, we test for arbitrary messages, for arbitrary keys. In this case, we don't really know how to optimize parameters for this type of keys. We don't have it in the estimator, for example. So this is just to show what you would have if these parameters were good. But in practice, you should have much better parameters than these. And this is actually an interesting line of work to follow to see really how far we can get with performance for this type of keys. Even though it's not optimized, this is already 2 times faster than non-amortized TF-HE, in terms of amortized time, of course. In summary, what changes if you think about few and TF-HE-like schemes, and without considering switching to other schemes, because we also have this possibility, but only for them, what we have is that this is basically gives one the first fully practical SIMD solution for these schemes. And by fully practical, I mean that we have performance improvements even for very small keys and very small parameters. We also are efficiently exploiting non-structured sparsity. And this is something interesting that other schemes are exploiting sparsity for a long time now, like SKKS, BFV, and others, they exploit sparse secrets. But for TF-HE and few, it was very limited. We have very limited ways of exploiting sparsity before this work. We also have very small keys, which can be very important, for example, if you think of hardware acceleration or things like that, or even just network communication. And our algorithm can also be parallelized if you want to improve latency, for example. For FHE in general, we also are presenting a practical RLW bootstrapping with polynomial noise. And there are practical advantages. Like I mentioned, the keys are very small. A key in a CKKS bootstrapping usually can go to tens of gigabytes, while our biggest key is just 71 megabytes. And compared to superpolynomial, it's still slower. Superpolynomial literature is way bigger than ours. But we are now at basically the same order of magnitude. We're only 2 times slower than other superpolynomial state-of-the-art methods. So finally, this is the amortized bootstrapping line of research. In addition to our work, there is also some other concurrent works this year. They are not really competing, they are more follow-ups of GPV23, which present very different asymptotics. And in general, they are both very interesting, and I'm also looking forward to see if we can combine these techniques and have even further improved performance. That's it. The implementation is available. The paper is to be presented at CCS. And thank you.